All right, nested quantifiers. So um, let's go through these. Again, another option of doing these yourself is starting with the symbols and translating each of these to words first and then doing the matching. That will take a bit longer, but it'll also probably be a little easier. I'm going to go straight from the statements, kind of rearrange it until it fits the pattern of one of these symbols. So first one, every course has an enrollment of at least one student. So what this is saying is for every course, why did I do that? For every course, for any course you mention, there's at least one student in it. So there exists a student such that the student is taking the class. For any class, biology, chemistry, discrete math, anyone you name, there's at least one student taking the class. Every course has an enrollment of at least one student. So we're looking for exactly this, and we find that here in G. G is for every class, there exists a student such that a student is taken. Second one, no student is taking every course. Well, that means any student that you come up with, there's at least one course they're not taking. So for any student you come up with, there exists at least one course that the student is not taking. This one's a bit trickier. Let's find this down here and then I'll read through it one more time. Right here. No. Right here, D. For any student you come up with, John, Bill, Ashutosh, Naraya, any student you come up with, there's at least one course such that the student's not taking the course. So this would be a D. Every student is taking at least one course. So this one I'm just going to go straight for every student you come up. So for every X, there exists at least one course such that the student is taking the course. So this is what we're finding here in C. For any student, there exists at least a course such that the student is taking the course. So this is C. There's a course that no student is taking. So there exists a course. There exists a Y such that for any student you come up with, the student is not taking a course. No one's in that course. There's a course that no one's taking. That would be F. No course is being taken by all the students. So that means for every course, there's at least one student that's not taking it. For every course, there's at least one student that's not taking it. And there is a student who isn't taking any course. There exists a student, there exists an X, such that for all Y, the student is not taking the course. That's B right there. Maybe pause, go back through those. These are very tricky. It's one of those things that with practice, that do get better and better. All right, one of these proofs to prove or disprove using any method of proof. I'll go ahead and do both of them. So part A, for integers a, b, and c, if c divides b a, then c divides a, or c divides b. So that one's false. And I'm jumping straight to the answer because I've played around with this. If I were you and I was starting the problem, I'd try several different A, B's, and C's first. But let's consider A equals 2, B equals 3, C equals 6. So what happens here, 6 does divide into BA, because BA is 6. 6 divides into itself. But 6 does not divide into 2, and 6 does not divide into 3. So because that single counterexample proves that this statement, this universal statement, is false. On B, if 6 divides M and 4 divides N, then 12 divides Mn. So let me go through the proof and then I'll show you true or false. So 6 divides M implies there exists an integer k, I'm just going to use symbols to shorten this a little bit, such that 6k equals m. And 4 divides n implies there exists an integer L. I'm going to use a different letter there because we don't need it to be the same one, such that 4L equals n. What we're doing here, we're just translating the divides into symbol into an algebraic equation. And why do we do that? Because then we can say then mn equals 6k times 4L. I'm just substituting what they equal here. And this equals 24KL, just multiplying it all together, which equals 12 times 2KL. Now, why is this important? Why am I pulling out a 12? Well, if I'm trying to show that this is true, notice this is mn, I need to show that mn equals 12 times some integer. Well, here I have 12 times 2KL, and to be rigorous here, by closure of integers under multiplication, what I'm saying here is if you take any two integers and multiply them together, you're going to stay inside the integers. You can't leave the integers. If you divide two integers, 2 divided by 3, you could go outside the integers. But closure of z under multiplication means you take any two integers, multiply them together, you stay within the integers. So 2KL is an integer, and 12 divides mn, because we have 12 times some integer equals mn. Now notice, A was a lot easier, right? Because all you needed was a single counterexample. And B, because it is true and it's a universal claim, you have to go through the hard work of showing that it's true in every case. All right, here we have a truth table. So an implication would be P implies Q, and contrapositive would be not Q implies not P. Logically equivalent, we're hoping that in our truth table, these two columns are going to have the exact same truth-false values. So let's set this up here. So we'll set up our first ones. I'm going to do these in red just to kind of show how they're a little bit different here. Probably didn't need the lines in red, but hey, we were grooving. So here I'm putting all 4 possibilities: true, 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 false, false, true, false, false. All right. And then P implies Q. Well, we can just get that directly. So we'll go ahead and put a column. Not Q implies not P. This will be a lot easier if we get not Q first and not P. And then we can get not Q implies not P. And again, what we're looking for, we want this column and this column to eventually add up. So P implies Q. This is going to be true unless there's a broken promise. What's a broken promise? A broken promise is when P upholds their end of the deal. So P is true and Q is false. So we're looking for a situation where the left side is true and the right side is false. The only time that happens is in the second row, so that's going to be a false, but the others are all true. The bottom 2 are called vacuously true because P didn't uphold there, and doesn't matter what Q does. Not Q is just going to take, the negation of Q is going to take each value in Q and flip it. Similarly, not P will flip each of the values in P. And now not Q, let me put a little dot there. So that's our left side, and this is our right side. We're again looking for the broken promise, but just with these 2 columns. We're not going all the way back to the original PQ. And not Q is on the left side. You have to be a little careful if the columns aren't in the right order. I intentionally did not Q first, so it'd be on the left side and not P is on the right. So we're looking for where the left side is true and the right side is false. This is the broken promise situation here. The rest are true. Since these truth values all match these, we know that the two are logically equivalent. So if you want to, that's probably sufficient what's happened already. This is the symbol for logically equivalent. It just means that if one is true, the other one's true. If one is false, the other one's false. All right, prove or disprove the sum of three consecutive integers. So let x be an integer. So we're letting x be any integer, negative, 0, positive, doesn't matter. Then x, we want consecutive integers at this point. So we'll take the one right above x and then the one right above that. So this is three arbitrary consecutive integers. They have to be locked in because the second one's always going to be one higher than the first, and then the third's always going to be one higher than that. And what I'm going to do is combine like terms here. So I'm going to get 3x plus 3, factor out a 3. So divisible by 3 means we have 3 times some integer. Since x, well, I'll say this. Since x is an integer, x plus 1 is an integer. Wow, that was horrible. All right, since x is an integer, which we assumed at the very beginning, then x plus 1 is an integer. So 3 divides this entire thing here. 3 divides any 3 consecutive integers. There's probably nicer ways to write that there, but that'll work for now. All right, there we go. Let me know if you have any questions.